It's hard to make predictions, especially about the future. A quote from Mark Twain is where we'll start out today's Cosmology segment. I'm your host, Dan, aka smAsho. And a quick little blurb here about Elon Musk. Elon Musk featured in this article here from space.com because Elon Musk will be hosting Saturday Night Live this week. And Elon Musk has downgraded his credibility in a lot of people's minds as he's offering $100 million to scrub carbon dioxide from the atmosphere. But he's hosting SNL, and the musical guest will be Miley Cyrus, so it should be a pretty highly watched episode of SNL this coming week. I figured I'd put that in today's Cosmology segment. And do you think Elon's going to go to Mars? Leave us a comment, let us know. And I mean personally. So today's opening quote from Mark Twain came from a phys.org article. Again, just to repeat that, it's hard to make predictions, especially about the future, said Mark Twain. But it's certainly true in the case of space weather. Part of the reason why we decided to start putting out lots of content on YouTube. What we didn't expect is to be able to forecast coronal mass ejections before they happen. Once again today, we see a little bit of that occurring. Can't really get into the way coronal mass ejections are forecasted, as it is the hinterlands. It is the complete cutting edge of I guess I'll say heliophysics without giving away anything too much. And I'll be writing a paper on the mechanism behind the solar polar field reversal cycles coming very soon. It's not really related to the forecasting of coronal mass ejections. I don't know if that throws you off or puts you onto the trail of what it is I'm talking about. That's fine. Many of our viewers are already well aware of the effects of solar storms on Earth's magnetic field, power grids, etc. And so obviously there's great value in being able to forecast coronal mass ejections before they happen. Not to mention on greater and greater scales. And you'll be able to understand heliophysics on a greater and greater scale if you understand the fundamental nature of things like stars. So we're going a little deeper than we expected into the rabbit hole of astrophysics, heliophysics, cosmology, and indeed geology on the channel, as there seems to be some vast misunderstandings when it comes to the roles of magnetic fields, as well as all kinds of other phenomenon. There's also a great video from Veritas included in here about the butterfly effect. If you haven't checked that one out, Veritasium rather, the fictional material where the channel is made of truth. So, and yeah, if you're watching the video Veritasium, drop me a line and we'll do a collabo. Some great video content out there from Veritasium. He certainly doesn't need our help. But in any case, space weather, let's just say it's difficult to predict. It's the reason I immersed myself in the data, and currently there's only about an hour to prevent disasters. Some coronal mass ejections send a shockwave of actual protons that arrive in only a half an hour. They're traveling at about 25% the speed of light. I won't get into that this time, as the major component of those coronal mass ejections would still be much slower in nature. Let's just put it that way. And without getting too in-depth into it, this article's on phys.org. Space weather, difficult to predict, with only about an hour to prevent disasters on Earth. And we do have spacecraft at Lagrangian point 1. So Lagrangian point 1 can transmit a slight early warning, but it only takes a handful of seconds for things like X-rays to reach the Earth. In other words, it's about 1/93rd the distance from the Earth to the Sun. So anyway, Lagrangian point 1 is where some objects are. And let's pick a random number to coincide with an object at the Neil Gehrels X-ray Observatory. Today's number is 232. And what might that be? It's B30650 plus 453, another catchy name for a quasar. So this quasar will most likely look like a spherical point of light, like an elliptical galaxy, because of the orientation of the galactic plane versus the viewer. Here are the X-ray outputs. Historically, we've got about 16 years of data for this quasar. Let's take a look at it on SIMBAD. And we'll look for a few different wavelengths here to see if we can spot that quasar. There it is in infrared light. So some heat radiation, making it to the 2 mass at least. And does it show up on the Chandra? That is the gamma ray right there. That's the Fermi. It's not a gamma ray hotspot. Does it show up on blue light? And there is a bit of a signal there in blue light on the DSS-2 in blue optical bandwidth. Let's go back to let's see if the Pan-STARRS has it. There it is on Pan-STARRS. That's probably the highest resolution view you'll see of that quasar. And just for you new viewers out there, if you're not aware what a quasar is, if you're viewing a galaxy, let's say it's a somewhat edge-on disk where it appears like cigar-shaped like this. The jets are coming out of this galaxy in this sort of a fashion. And if you're inside the jet, that galaxy would likely to be a quasar or a blazar or a Seyfert 2 galaxy if it's over here. And if you're viewing it from over here at this sort of an orientation, it would be a radio galaxy most likely, as those other frequencies are largely blocked by the galactic disk. So a quick little explanation of what a quasar is. It's all about orientation and perspective. That's B30650 plus 453. Today's random cosmology segment object. Today's random, it's not really random. NASA chooses it. The astronomy picture of the day is I believe it's a Redstone 2 rocket. And you can see there the candle's been lit, is the quote. Redstone 3 rocket. That was back on May 5th, 1961. Which took Alan Shepard to an altitude of 116 miles and a speed of 5,134 miles per hour. Later, he would take a very famous photograph of the Earth from re-entry from the moon. But there's the candle being lit all the way back in 1961, NASA's photograph of the day. And I wanted to revisit this article here, as there is an issue with this that I must address in today's Cosmology segment. So this galaxy is part of a cluster of galaxies. It's located at about 600 million light years estimated distance. And I just wanted to note something from the artist's rendition here, because there's a portion of this that makes no sense. So what this article is about these 90-degree bends in these jets. So now we've seen a lot of galactic jets, folks, that have significant jets emanating out of the cores of the galaxies. I'll just say the cores of the galaxies. And before we continue, ignore this completely. This is a foreground galaxy that has nothing to do with this galaxy. It's at a completely different focal distance, focal length, distance, whatever you want to call it. And anyway, this galaxy has 2 jets. And you can see right here there's one oriented like this, and there's one oriented like this. Those are the polar jets of the galaxy. They tend to emanate from the poles of those galaxies. And for some reason, this artist rendition has this jet here. This has nothing to do with what we're seeing in the imagery. So I have no idea why this is even here. This has nothing to do with what this would look like. So if this is this turned 90 degrees, I don't even know what this is supposed to be about. I don't know why they have this jet here, because as you can see in this image here, there is no jet oriented like this. And there's no jet oriented like this. So I have no idea what this is supposed to be about. But in any case, if we could see the galactic disk associated with this galaxy right here, the toroidal field would be like this. That would be the way the donut-shaped portion of the galactic disk would be oriented. For example, if it was a spiral galaxy, it would look like the arms would be sort of like in that orientation, and the jets would likely to be perpendicular to the galactic disk. As we see in most galaxies, you see roughly perpendicular jets. So since the jets are oriented like this, that gives us insight into the plane of the galaxy. So if this is you would expect the galaxy to be oriented like this. This would make sense. What the article is about these 90-degree bends in the jets, as we're not sure how that's a thing. And my guess is that there is a smaller galaxy forming up here where these jets slow down sufficiently to condense into large groups of stars. So I think there's a globular cluster where I put each of these X's, and that is why you're getting these 90-degree angles. Also, I believe this galaxy is extremely symmetrical, which is why these jets are so similar. Because you can see the length of the jets is similar. Each one is about 16,000 light years in length. And again, this is at a distance of about 600 million light years. I just wanted to revisit that because this image over here has nothing to do with what we're seeing on this image over here. This jet here simply isn't reflected in this image. So I don't know what that's talking about, but I just wanted to revisit that. That is from an article you'll still see on phys.org, a new window to see hidden side of magnetized universe. I'll let this one scroll again in case anybody wants to read the article. Let's talk about pulsar motion. So we've talked about pulsars before on many of our previous cosmology segments. And on previous cosmology segments, we've also even talked about things like neutron stars behaving like comets, moving at hundreds of kilometers per second, nearly the speed of the solar wind, and so on. So really what we're looking at here is the disparity between the center of the supernoval nebular remnant and the location of a pulsar. So we see this pulsar, and you can see its spin angle versus its velocity. You can see it's moving away from the center of the supernoval remnant, and this is not understood. So the reason why there would be such a disparity between the location of the center of the supernoval remnant and the location of the neutron star, perhaps it's because it's a moving neutron star. You can see it looks almost like it's hollowed out a portion of the supernoval remnant right in here in a roughly hourglass-shaped area. You can see a void-like region there in the center. So maybe this thing is moving on a curved path? Just saying. But in any case, a significant disparity between the location, spin, and velocity of the pulsar J0538 plus 2817 with respect to the supernoval remnant nebular cloud which it occupies. So that may get some wheels turning in people's minds, but in any case, another article here on phys.org about it. Detected by FAST, which is, I believe, one of the radio telescopes. As more and more data is coming in to the point where it's hard to keep up with the stories. They got three-dimensional velocity by combining the transverse velocity measured by very long baseline interferometers. So very large ground-based radio telescopes are what enable such things Fantastic view there of this supernoval remnant and some of the workings therein. Pulsar J0538 plus 2817. I say we give it a better name. Leave us a comment. Let us know what you think it should be called. And let's talk about the cosmic web. Why are some places so homogeneous and why other places so unhomogeneous when it comes to the structure of the universe? So there's a certain sort of a fractal nature that happens when you look at the universe from the perspective of about 300 million light years resolution. However, when you look at it from different perspectives, it's sometimes much more and much less fractal than it appears. Why is the universe so homogeneous in some places and so unhomogeneous in others? Does it give us vital information as to the mechanisms associated with it? Why is it that some things look like fractals at nearly any scale and other things absolutely not? Void regions of the universe, for example. Void regions are absolutely nothing like the cosmic web, the fact that some galaxies seem to be highly connected and that there appear to be strings of material in between the galaxies in many cases. Why is it that some stars appear as strings of pearls and other ones absolutely not? In fact, most absolutely not. But in any case, it's super interesting to consider what it is that it tells us about the fractal nature of the universe when looking at the homogeneity and inhomogeneity of portions of the universe at different scales. Some things are very much alike, and some things are very much not alike. And that's today's Cosmology segment. We hope it was unlike anything else you've seen in recent times.